So in this section, we introduce the principles of link state routing through OSPF. OSPF is an interior gateway protocol, or IGP, designed for IP networks that is founded on the principles of link state routing. The link state behavior provides many alternative advantages for medium and even large enterprise networks. Its application as an IGP is introduced along with information relevant to the understanding of OSPF convergence and implementation for supporting OSPF in enterprise networks. So upon completion of this section, it is generally expected that trainees will be able to explain the OSPF convergence process, describe the different network types supported by OSPF, as well as successfully configure single area OSPF networks. OSPF is a form of dynamic routing protocol that is classified as a link state routing protocol, which generally refers to the typical role that a router will play for each link it is connected to, as opposed to having a single role that applies to all links. As a dynamic routing protocol, OSPF includes a vast number of improvements over RIP. However, with it comes a greater level of complexity. OSPF-enabled routers contain link state databases that contain information of the routes within the OSPF domain from which the routing entries in the IP routing table are populated. If a change in the topology is needed, the route changes are performed based on the routes contained within this database. Communication of routes is as such minimized to events where routes are added or removed to or from this database. This is somewhat different from the need for the best routes to be periodically advertised every 30 seconds as found in RIP. With OSPF, a one-time update of all routes is made that the router uses to determine from its own perspective the best path to each network. This behavior also allows for rapid convergence in the event of link failures, since the information needed to determine a new best path is already present within the OSPF link state database of the router. The calculation of a new best route relies on greater use of router resources, however. The protocol is also considered hierarchical, which allows for a greater level of scalability, but also is capable of operating over other protocols, such as a protocol known as MPLS, that helps to bridge the communication of the same OSPF autonomous system over geographically dispersed locations. Routing decisions are based on a more accurate metric system that does not only consider distance, but also the factor of link capacity, which determines how much data can be transmitted per second. The convergence of an OSPF network requires that all routes be known, from which decisions about the best path for each network are determined. This information is collected from neighboring routers when routers become active within the OSPF domain. Advertisements similar to those seen in RIP are used and are referred to as link state advertisements, or LSA. These are used to carry the route information to the neighboring routers. The information received is stored within a link state database within the receiving router. Once the link state database is populated with the known routes of all routers within the OSPF domain, an algorithm known as the shortest path algorithm, and at times referred to as Dijkstra's algorithm after the man who discovered the formula, will be used to calculate the best path to each network, with the router in question acting as the root location in each case. These best routes are then used to populate the IP routing table. If a best route fails, the router will return to the link state database and recalculate a new best path, which invariably takes up system resources but greatly speeds up the convergence process. Each router active within the OSPF domain must be assigned a router ID that is used to uniquely distinguish the router. This router ID is a 32-bit value that can be manually configured or represented by an existing IP address within the router. The highest address present in the router will be taken as the router ID, any loopback address will be primarily used, and the address of a physical interface used in the absence of a loopback address. Manual configuration of the router ID, however, is generally recommended. The physical topology of an IP network has a large impact on the way in which the network behaves. Networks that operate over Ethernet are considered by OSPF to be broadcast networks, and will therefore apply a certain mode of operation specific to broadcast networks, of which we shall look at in more detail later in this section. Any OSPF network formed over Ethernet will therefore automatically assume the broadcast OSPF network type. We can also consider the case of where a network is formed solely between two devices in what is generally understood to be a point-to-point form of network. In this instance, we generally find where Ethernet is used, the broadcast network type is again applied by default, following the general rules as we have just seen. Where dealing with serial, however, we find that the adopted OSPF network type is set as point-to-point by default. Serial networks support data link operations through protocols such as PPP and HDLC, for which the point-to-point network type is applied, regardless of which serial-based link layer protocol is used. There are some additional legacy network types that are also supported by OSPF that operate over legacy link layer protocols such as asynchronous transfer mode or ATM and frame relay. These represent the underlying protocols for networks like those we see here, involving special frame relay or ATM switches. Communication is built over circuits that represent a connection between two endpoints, similar to the form of connection made during telephone calls. Two forms of OSPF network type may exist in these cases, such as non-broadcast multi-access or NBMA and point-to-multipoint. The point-to-multipoint network type behaves similar to a point-to-point network. However, each point-to-point circuit represents a separate network with separate addressing. The NBMA network type, however, operates in a similar manner to a broadcast network, although it's not a true broadcast network. Communication is in fact unicast, but replicates the packet and forwards the replicated packet to support multi-access type network behavior. In all broadcast networks, a router is assigned as a designated router to manage communication of routing information, and we see this also occurring within NBMA-based networks. The establishment and maintenance of the OSPF link state behavior for a given network segment, such as the broadcast network segment that we see here, relies on the election of a router as a designated router for the segment. The purpose of this is to better manage the communication of OSPF packets within the segment. The designated router is supported by a backup designated router in the event that the designated router fails. Packets from all other routers will be transmitted to the designated router and backup designated router that are listening for OSPF packets with a multicast address of 224.0.0.6. The designated router will be responsible for transmitting these packets back to all other routers that are listening for OSPF traffic with a multicast address of 224.0.0.5. Communication can be understood by the formula of n times n-1 divided by 2, which represents the number of communication flows that exist. If no designated router existed, a set of 4 routers participating in OSPF would establish 6 separate flows of communication to share OSPF database information with all neighboring routers. With the presence of a designated router, this is reduced to 5 separate flows, based on the same n times n-1 divided by 2 formula. As the number of routers increases, however, the level of effectiveness of the designated router increases also, allowing traffic flows to be optimized. The relationship of the links between OSPF-enabled routers can represent one of 2 forms, either a neighbor state or an adjacent state. The effect this has also relates to the operation of the router on the link. We have already introduced the designated router and backup designated router. However, a third and final type is known as the DR other, which represents all links that do not operate as either a designated router or DR, or backup designated router or BDR. The neighbor state is established in recognition of another router on the link. However, OSPF routes in the link state database are not communicated between such routers. The adjacent state, however, may at times also be understood as a full state, in which routers that establish such a state will communicate all link state database information with the peering router. In the case of the designated router, it will establish an adjacent state with all routers that allows the link state database of all DR other and BDR to be known by the DR. The DR will then be responsible for acting as a central point of communication for all link state database information, ensuring all routers have identical and complete link state databases that are used to calculate the best path to every network by each router in the OSPF topology. We demonstrate here the link states from the perspective of RTA, and how each link represents either a neighbor or adjacent state with the peering OSPF routers. How these neighbor states are established is based on a process of link states that each link goes through in order to achieve either a neighbor or adjacent state. Every router will begin in a down state, meaning that no hello packet has been received. If the network type is NBMA, the link of the router will move to an attempt state to attempt to discover neighbors by sending hello packets periodically. For all network types, the links of routers will transition to an init state at the point that a hello packet is received from a peering OSPF router, but does not represent that the router is aware of the peer just yet. When the peer recognizes the neighbor, it will carry the neighbor's router ID in the hello packet. At this point, the router will need to decide whether the link state should be either a two-way state or should begin the exchange start process. It is also at this point that the DR and BDR can be determined. The links for routers elected as DR and BDR will proceed with the exchange start process. DR other router links that peer with the DR and BDR will also transition to the exchange start state. Links between DR other routers will settle in a two-way state and be considered as having a neighbor relationship. They have established bidirectional communication, however will not directly share link state database information. Those links that move into an exchange state will in summary begin the process of establishing adjacency through sharing the contents of their link state databases. This particular state concerns with building synchronization between the peering links and discovering a master and slave relationship between the peering devices. Once this relationship is decided, the exchange state will begin, in which peers will exchange information describing the contents of their link state database. The peering router will use this to identify which routes in the database of the peer the local router does not have a copy or an up-to-date version of. Once this exchange is complete, OSPF routers must request the outstanding route information in full from the peer that is not present in the router's own link state database. The completion of this process signifies the end of the loading state and a full state of adjacency is formed, in which peers have identical link state databases. Here we look in more detail at the process of neighbor discovery that occurs during the init state. This involves the communication of hello packets between the peering OSPF routers. The hello packet contains the format as shown here, in which an interval for the hello packet is defined. This interval by default is set to 10 seconds, and both peering routers must have matching hello intervals in order for discovery to be successful. It is also within the hello packet that we find the priority that is used to elect the designated router and backup designated router. Once these are discovered, the router IDs of the DR and BDR are carried within the respective designated router and backup designated router fields. The dead interval represents the duration that an OSPF link will wait before considering that the peer has been lost. The interval is 4 times that of the hello interval, which by default is 40 seconds, and the gain must be the same on the peering links of communicating routers. Once bidirectional communication is achieved, the router ID of the receiving router is included in the neighbor field of the hello packet. It is at this point that routers transition from an init state to either a two-way state or an exchange start state. The hello packet may contain the router ID of one or multiple neighbors. After the discovery process is complete, it is possible to determine the designated router for the segment. This will only occur, however, where the network type is either broadcast or NBMA. If we take a look at the example given, we can see that where Ethernet is used, the network type by default is broadcast, and that a designated router is generated for each segment, and not for the autonomous system as a whole. The priority primarily determines the designated router for the segment, and in this instance, the priority value of 255 asserts in this case the interface of RTC as the DR for the segment connecting RTA and RTB, and RTD as the DR for the segment connecting to RTC. Since the segment between RTC and RTD represents a point-to-point topology, it is generally good practice to change the network type to a point-to-point type so as to minimize traffic that would otherwise be generated by the DR. A point-to-point network, if we recall, will not elect a designated router. Where a designated router is elected, it is also necessary for a backup to be determined. The next best priority will determine the backup designated router. If priority values are equal, the router with the superior router ID on a loopback interface takes on the role. As with the DR, the BDR forms an adjacency with all peers, which allows it to immediately take on the role of DR should the current DR fail. The priority of 0, however, will prevent a router participating in the election, and so can be manually set for routers that are not to become a DR in the OSPF domain. One last thing to note is that the segment between RTC and RTD is now set as point-to-point, and so the DR on this segment is no longer present. The exchange start process that follows the init state will see the peering routers compete for the role of master and slave. This is to allow a single router to manage the exchange process in the relationship. The role of master is determined by the router ID, in which case a higher value represents superiority. We would expect here that RTB therefore take the role of master. Negotiation is performed using empty database description packets that contain 3-bit fields known as the initialize, more, and master-slave bits, along with a sequence number. We see here that RTA has attempted initially to assert its position as master, and will set a sequence number that is expected to be used as part of the communication process. RTB, having the better router ID, however, doesn't accept the role of RTA as master, and returns its own database description packet declaring itself as master for the segment, with a sequence number defined by RTB. RTA concedes and takes on the role of slave, reflecting the sequence number of RTB to show compliance. Immediately following this, the exchange of partial link state advertisements will begin as part of the exchange process. This is used to only inform of the contents of the link state database of the neighbor, so that only the required information can be requested. Once the peering routers have a clear record of the neighbor's link state database, the peer can request the required link state advertisements to allow the databases to be identical. The router possesses a list known as the link state request list that it uses to determine the full link state advertisements it needs to request from the peer. A link state request packet is generated for this information and sent to the peer, who will provide the required link state advertisement in a link state update packet. As each request is completed, it is removed from the link state request list until no more requests are necessary. It is at this point that the device is able to transition to a full state. While the RIP protocol was seen as using a metric based on hop count, the OSPF metric is based on a factor of cost, which relates to the bandwidth that the link is capable of supporting. We calculate the cost of a link based on two factors. One is bandwidth reference and the other is actual bandwidth, measured in megabits per second. The bandwidth reference plays an important role in ensuring the accuracy of the metric. A formula is used to determine the cost based on a factor of bandwidth reference divided by bandwidth. The higher the bandwidth reference, the more accurate the metric is considered to be. The default 10 to the power of 8 bandwidth reference may not clearly distinguish higher speed links, and so we can use the bandwidth reference command like we see applied to OSPF process on RTB to enable a better distinction where higher bandwidth is supported. Alternatively, the cost value can be manually defined in the interface view using the OSPF cost command as shown here for RTA, in which the cost metric is set to 20. The convergence of the link state database provides each individual router within the OSPF domain effectively what is a map of the entire network topology, via which each router is capable of independently determining the best path to each and every learned network. A failure in the network does not require that the router relearn the best path from other neighbors. Instead, the router will determine from the link state database any alternative best path that is available. In this instance, we can see how RTC is able to determine paths to networks 10.0.0.0 and 20.0.0.0. In the case of the 20.0.0.0 route, RTC has discovered equal cost paths to the same network, and therefore has implemented equal cost load balancing over the two links. Currently, we are only dealing with a small number of routers within the OSPF domain. This means the current link state database is manageable, and a link failure, let's say between RTA and RTB, is still recoverable without too much impact to network resources. Such smaller OSPF networks will operate as what is known as single area. This can be understood as a flat structure for which all routers operate using identical link state databases. As part of the configuration, we will notice that an area needs to be defined. Where a single area is used, any number can be assigned. However, it is generally recommended in the interests of good design practice that this be set as area 0. As the size of the IP network managed by OSPF increases, so does the link state database. The ability to converge larger databases that involve perhaps 50 to 100 routers begins to have a greater toll on the resources of each router and the size of the stored link state database. With a larger number of networks, the potential for failures and changes in the network drastically increase, and any change will in fact impact every router in the OSPF domain. The effects of reconvergence and resource utilization may result in performance issues, and even loss of data if network traffic is heavy. The use of multiple areas allows for changes or failures in one area of the OSPF domain to be isolated to that area, and limits the impact to other areas. It also allows for the link state database to be reduced in size, with routers containing a link state database relevant only to the area in which they are located. Certain routers that are found existing in more than one area will maintain link state information of the areas in which they reside, and act as a border router for these areas. One key point to note is that these OSPF areas operate in a hierarchical manner, for which area 0 represents a form of transit area. This design requires that communication between all other areas traverse area 0, so as to prevent routing loops from forming within the OSPF domain. The establishment of a router as part of the OSPF domain is demonstrated here and requires initially that the OSPF protocol be defined along with the process ID. Separate process IDs will generate separate link state databases, and so it is recommended that the same process ID is used throughout. If no process ID is specified, process ID 1 will be used by default and is reflected in the parenthesis for the OSPF protocol view. Following the process ID, the router ID is manually specified, for which in this case is set to 1.1.1.1. It is not compulsory to set the router ID, but it is recommended. Once the protocol view has been entered, it is necessary to specify the area within which the router will operate. We focus on the use of single area OSPF here, and so we define area 0 as the area to be used. The parenthesis will then include the area ID, which is represented as a 32-bit value, similar to the way the router ID is represented. The network command identifies the network that is to be advertised into area 0 by the router, and is followed by an inverse subnet mask that is known as a wildcard mask. In this case, bits that represent the network address are assigned with a value of 0, whilst those which are not fixed and represent the host are represented by bit values of 1. For the 24-bit mask in OSPF, the 0.0.0.255 wildcard mask is used. Through the display OSPF peer command, we are able to determine the current peer relationship between the OSPF-enabled routers. The information displays the details of RTB from the perspective of RTA, that is represented by the router ID 1.1.1.1. We are able to determine through this display command the router ID of the neighboring router, as well as its status as either the master or slave when negotiating adjacency. As the router with the higher router ID, the neighbor is assigned as the designated router for the segment. This occurs as the segment is currently operating based on the default broadcast network type. In order to reinforce security of the connection and prevent rogue devices from being introduced into the OSPF network, the use of authentication is configured within OSPF. This can take the form of simple plaintext or cipher, or using cryptographic algorithms for authentication in the form of a message digest algorithm known as MD5. We show here how authentication is applied to the interface Gigabit Ethernet 0/0/0 of RTA. Once under the interface view, the command OSPF authentication mode is used to identify the form of authentication to be used, as either simple, MD5, keyed MD5, or null, where no authentication is applied. Here we use MD5 to carry authentication using a cryptographic hash digest. If we use the debugging function of the router, we are able to follow the flow of authentication that is being performed. The highlighted information here shows the authentication type being used over the link that must match the peer's chosen method of authentication. An authentication type of 02 reflects the MD5 authentication. Along with this is the key that is used. However, due to using MD5, this password is hashed and therefore not visible over the link. One final feature that reinforces establishment of the OSPF domain is the silent interface. This command can be used to disable the communication of OSPF packets over an interface. In doing so, the OSPF domain prevents adjacencies from being formed with non-authorized rogue devices. This is basically achieved since OSPF hello packets are prevented from transmission over the silenced interface. If we display information for the interface that has been silenced, we find that the interface is operational. However, communication is isolated. Incidentally, we find that the interface is now only able to see itself, and that the state of the designated router is associated with the local interface. More importantly, however, is that we are able to verify the status of the interface as silent by the highlighted silent interface no hello status display. This then brings us to the summary for this OSPF section, which we have a couple of questions here. The first asks, what is the purpose of the dead interval in the OSPF header? Well, we can understand the dead interval as being a timeout mechanism that determines how long an interface will wait before assuming that the neighbor relationship is inactive. Once the dead interval timer expires, the neighbor relationship will be terminated. In a broadcast network, what is the multicast address that is used by the designated router and backup designated router for listening for link state update information? The DR and BDR will listen for updates on multicast address 224.0.0.6. All other routers will use the multicast address 224.0.0.5.